basic concepts of measurement methods. I am going to provide a brief introduction to this topic. We make measurements every day, and measurements such as temperature at home, filling up gas at a fuel pump, etc. So what are the objectives here in making these measurements? So the objective in any measurement is to answer two questions. First, how can a measurement plan be devised so that the measurement provides unambiguous information we seek? The second question is, how can a measurement system be used so that the engineer can easily interpret the measured data and be confident in their meaning? So these are the two questions we must ask ourselves in any measurement that we make. So specifying a measurement system and measurement procedures represents an open-ended design problem whose outcome will not have one particular solution. So in other words, if we want to make a measurement, the measurement system and the procedure involved in carrying out that measurement represents an open-ended problem. That is, there are numerous ways to get to the objective. What that means is that there might be several approaches to solving a given measurement problem. Some might be better than others, some might be more involved, some might give quantitative results, some might give qualitative results. So we have to weigh the pros and cons of each measurement method and decide which is the best measurement technique that we are going to adopt. In order to answer the two questions posed in the previous slide, we need to design an experimental test plan. So what is an experimental test plan? An experimental test plan is the way an experiment is designed and executed. And there are three components to this. The first one is called a parameter design plan. So what are the parameters that you would consider before you start the experiment? So in other words, what are the questions that you're trying to answer by carrying out this experiment? What are the parameters that you need to measure? So these are the two questions that you have to ask yourself before even starting an experiment. And the second component of the experimental test plan is the system and tolerance design plan. In other words, how good do the results need to be? Or what is the error that you would be comfortable with in your experimental data? So that has to be known a priori. And the third component of the experimental test plan is the data reduction design plan. That is, how are you going to interpret the data that you acquire from the experiment? And once you analyze that data, you have to ask yourself, does the answer make sense? So this is, in a sense, or very briefly, what an experimental test plan is. So once you have your experimental test plan, you need to set up your experiment, or in other words, you need to set up your measurement system. And here we see the components of a general measurement system. So a measurement system is composed of different stages. The first one is the sensor stage. So the sensor stage is the stage where the physical process is being sensed. So what is the physical process? It could be the process could be temperature, pressure, or any such physical phenomena that needs to be sensed or measured. So a sensor measures that physical phenomena and then sends the signal to a transducer, and a transducer converts that physical the signal that is sensed by the sensor, the physical phenomena, into an electrical signal. Then the electrical signal passes through a signal conditioning stage. So in here you can have amplifiers and filters to condition the signal. So once the signal is conditioned, you can then write the signal or record the signal using data acquisition devices. So that is called the output stage. Some measurement systems also have a control stage. So control stage is basically it is part of a feedback loop that provides the output signal as a feedback to the sensor to control certain aspects of the measurement process. So this is in general or a basic schematic of a measurement system. And we have to remember that before we use a sensor, it needs to be calibrated. And I'm going to explain the process of calibration now. So calibration is the process by which we apply a known input to a measurement system for the purpose of observing the system output value. For example, if we want to calibrate a load cell, what we can do is we apply a known input. So let us say 1 pound. So we apply 1 pound on the load cell and then observe the output of the load cell, which would be in volts. So we are basically trying to establish the relationship between the known input and the output of the load cell. So that is, we are trying to establish the relationship between the load applied and the voltage output of the load cell. So the known value that we input to the system is called the standard or the reference value. So in any calibration process, the input that we apply has to be a standard input or a reference input that is not subject to change. So what is the purpose of this calibration process? So it is the essence, as I just mentioned, is to establish a relationship between the input and output. So on the right hand side, if you look at the image, the curve, the x-axis is the input, y-axis is the output, and the relationship between the known input and the output can be described in terms of the curve y equal to f of x. This is called the calibration curve. So what is the purpose of this calibration curve? So let us say we want to use the load cell in an experiment, and we calibrated the load cell and we obtained the calibration curve. So we want to know what is let's say the load that the load cell is going to measure, or the load cell or the force in any given system, let us say, and we are using a load cell to measure that force. So when we use the load cell in an experiment, when we connect it as part of a as a part of a measurement system, all we are going to record from the load cell or the output of the load cell is going to be recorded in our computer or using a data acquisition system. The output that we record is going to be in volts. So now we can use that output, put it into the calibration curve, and once we do that, we can know, or we can obtain the force that the load cell actually measures. So that is the overall objective or the purpose of calibration. So it is such that, to restate what I've just said, the correlation or the calibration curve can be used in later measurements to ascertain the unknown input, which would be the force that we want to know, based on the output value. So that is based on the voltage that we recorded. So that is the value that is indicated by the measurement system. We also have to remember that in any measurement there are errors involved, and they can be categorized as random and systematic errors. So by combining the random and systematic errors, we can obtain what is called the uncertainty in the measurement. So the errors are effects that cause a measured value to differ from its true value, and a random error causes a random variation in measured values found during repeated measurements. So if we repeat a given experiment number of times, there will be a scatter in the data, and that scatter can be quantified using standard deviation, and that defines, or that gives us the random error in the data. Systematic error causes an offset between the mean value of the data set and its true value. So that is this is the deviation of the average value of the experiments that we carry out from the true value of the experiments. So combining random and systematic error, we can obtain the uncertainty in the data, which we are going to discuss in later chapters. So here on the top, I show a brief illustration of what random and systematic errors are. So here we throw the darts at the try to throw the darts at the bullseye. In figure A, you see that all the darts are focused at a given point. In other words, there is high repeatability. That means the random error is low, but it doesn't tell anything about the accuracy because they are far away from the bullseye. In figure B, all the darts are right inside the small circle, inside the bullseye. So that means the accuracy is very high, and the random and systematic errors are very low. In figure C, you can see the darts are all over the place. So in other words, the random and systematic errors are very high, and therefore the accuracy also is very poor. To summarize, a measurement is the process of asking a question. A measurement plan is then developed to answer that question. So measurement systems in general consist of sensors and transducers, signal conditioning devices such as filters and amplifiers, data acquisition devices to record the output, and feedback control in some measurement devices to control a measurement system. The sensors and transducers are calibrated prior to any measurement. So this is required for us to have accurate and dependable measurements. And the calibration is the means to relate a measured input value to the measurement system output value. And a measured output signal can be affected by many variables that will introduce variations and trends and can confuse the answers, and all these errors can be categorized as random and systematic errors.